I hope you had some good rest overnight. You didn't study too much. Trust me, it is a marathon, is not the race, so please be aware of it, or you burn yourself out. And use these mock exams. I just found that out. It's a great opportunity for you to kind of see what do we do. You're kind of first generations we're doing this with, and I think it's just an awesome opportunity for you to kind of feel that exam anxiety, and you'll have me in a corner yelling and spraying water at you while you're answering the questions. Those are little things. No, I won't be there. But so now we're back to our next lecture, and today we're going to discuss the structure and function of cell membrane. So we're going to go more specific now in talking about the cell. And we're going to start with a case. And I'm not going to paraphrase the entire case. You can read it to yourself. This is actually a case that was reported some time ago in a medical journal, where you have a 55-year-old male who has no significant history or problems. Medical history shows up in emergency department with problems. He feels dizzy. He starts feeling weakness in his left arm and both lower limbs. This individual eventually becomes more weaker and progressively weaker and have problem talking. During the process of interview, he actually says, only thing I remember is that a couple of hours ago, actually an hour ago, I visited a local sushi place, okay? And in that local sushi place, I looked at the menu. It's not really the best place I've seen, but the menu, there's something called Usujukuri Tessa. And so it sounded really cool, so I ordered it, and I ate it, okay? And it's the only thing that I remember that I've been doing in the last couple of hours. This individual now progresses further into more respiratory difficulties, becomes fully paralyzed, and eventually has to be placed on the respirator to breathe. So he is also treated by washing his stomach out with stomach lavage. He's been given an active charcoal to remove toxins. And what's the most likely diagnosis? You probably know. He ate a pufferfish. Okay, so he ordered, if he read that name and translated it into Japanese, he will realize that's a pufferfish sushi. Pufferfish produces tetrodotoxin, which is a very serious toxin. It's around 1,200 times stronger than cyanide. Okay. It's really, really strong. And what's a characteristic that it causes? A paralysis of muscles and nerves. It will inhibit the activity of special transporter. We're going to mention a channel today known as sodium channel, voltage-gated sodium channel. So these individuals will not be able to transmit impulses to their nerves, and they will not be able to contract their muscles. So this is a characteristic of it, and death usually can occur from paralysis of respiratory muscles. Now, when you go and visit Japan, don't freak out. You can actually eat pufferfish, because now they can sell you non-toxic pufferfish, because they realize that the reason why wild pufferfish cause these issues are because they eat a specific type of algae that carries tetrodotoxin in it. So if they grow them outside in controlled environment, they are not toxic whatsoever. What's a therapy? There is no therapy. Therapy is you put them a respirator, you try to get rid of the toxin, and eventually they'll get better as their body eliminates the toxin. So that is one of good examples of the cell membrane function. I'm going to show you that in a second. So what is the cell membrane? Cell membrane, or also known aka as a plasma membrane, is selectively permeable outermost structure of the cell. What does that mean? It means it's the skin of the cell. It's around the cell, okay? And it regulates what goes into the cell and out of the cell. So it is selectively permeable. It's very, very active structure and regulates the transport in and out of the cell. And its function is this. It has membrane lipid proteins, have lipids and proteins in the membrane, and these are involved in several things. They can regulate transmission of signals from the outer environment. So membrane can be a place where signals are transmitted from outside into the cell. Membrane also acts as anchorage point for, you remember those cytoskeletal proteins that are inside the cell that form a skeleton of the cell. We're going to talk about that tomorrow. So their skeleton of the cell will attach to inner portion of the membrane, and they will also attach to the extracellular matrix, or a skeleton outside the cell that will hold the cells in their location. So that is a very important function of the membrane. So let's look at what forms the membrane. Three structures. Number one are phospholipids that will form these two anti-parallel sheets, one and the other. These little things that have heads at the end and two tails, those are phospholipids. The next is cholesterol that we see here, that is much more geometrically complex, is actually located between the phospholipids, and we see it here. And proteins are inside the membrane, and then they enable the function of the membrane. So when we look at this, we'll see that the membrane has two layers, two leaflets. It has the one that is much closer to the cytosol. This is cytosol, this is inside of the cell, and this is known as the inner leaflet of the membrane. And there is another one that is another leaflet that faces outside of the cell, and this is known as the outer leaflet of the membrane. So membrane has two leaflets. See, there are two layers. One is facing the cytosol, another one is facing the outside environment. So what is the most abundant structure that forms the membrane? Most abundant molecule that forms the membrane are lipids. Remember this. So the membrane is pretty much full of lipids. So lipids are a major component of the membrane. Now the three types of lipids will form a membrane. Phospholipids, they're most abundant. We showed them with little heads and two tails on the bottom. Next one is cholesterol. We showed it too. And another group are glycolipids, which means they're lipids that have attached carbohydrates to them. So first one is phospholipids. We see them here. These are the phospholipids that form the membrane. So what's a characteristic for a phospholipids? They are really weird. What does that mean? Is that they are polar ionic compounds that have amphipathic nature. What does that mean? That means that one portion of the phospholipid likes water, another portion of the phospholipid hates water. So they can't make their decision. You know, they like two gals or two guys. You know, they can't really make decisions. So there is one portion likes the water, another one hates it. So that is the characteristic of these phospholipids. So what makes them having this weird nature is they have hydrophilic or polar heads. This blue circle that you see on the side, on the right side of the slides. And this is a polar portion. It means it has a charge. Look, plus, plus, plus. These charges make them like water. Whenever they're polar, they like water. So this is the hydrophilic or polar portion, also known as the head. Those little heads you've seen on that image before. They consist of phosphate that's attached to alcohol, specifically attached to serine and tanolamine, inositol and choline. So they will form phosphatidylserine, phosphate attached to serine. You see here, phosphatidylserine, phosphatidylethanolamine, phosphatidylcholine, and phosphatidylinositol are the ones that are actually heads of these phospholipids. Next is a backbone, and the backbone is formed by glycerol. And then the next portion is hydrophobic, is the portion that hates water. And this is a non-polar portion. It does not have any of the charges on it. And it is formed by long hydrocarbon, actually long fatty acid tails. Fatty acids will have these tails. And why they don't like water? When does the fat mix with water or oil mix with oil? Never. Okay, so these portions hate water. They're hydrophobic. So let's look at this. First is how they are then organized in your membrane. Number one is these hydrophilic or polar heads will what? They like water. So these heads will face towards water. Okay, so they will extend outward towards the environment, while hydrophobic portions, these fatty acid tails, will extend inward towards the center of the membrane. Now there is a characteristic of these hydrophobic tails, And it is that they're made from fatty acids that can be saturated and unsaturated. Saturated means they have no double bonds. Unsaturated means they have double bonds. These bonds can be eventually broken if you want to. So so saturated are stable, while unsaturated are unstable long-chain fatty acids. Now, fatty acids are really cool. Those little tails on the bottom, they move. They actually dance all the time, okay? So what is the characteristic of that movement is that these fatty acid chains can flex, do some flexing. They can rotate, spin a bit, okay? And they can have some lateral movement doing this, okay? So that is the characteristic for them. However, if these fatty acids have double bonds, think of it as kinks in their little tails, so they do not move that much, okay? So they become very much tight. And what does they do? The kinks in the chain will reduce motion, their motion, and these kinks in their chain, these double bonds, will prevent fatty acids from packing really tightly together. It will kind of form the space. And so this is it. So please remember that phospholipids that are anchored in a membrane, in an inner leaflet and outer leaflet, do not change leaflets normally. So the phospholipid that is in an inner leaflet does not pop out on the outer leaflet and vice versa in normal situation. So next one we're going to talk about is cholesterol. So is it always bad? No, we actually need cholesterol for functioning of our cells. So the cholesterol is also an amphipathic molecule. One portion likes water, another one does not. It's dispersed throughout the cell membrane. We see it here. And it has two groups. It has this hydrophilic group that is polar, and this is this hydroxy group at the end of the cholesterol. And this is the one that faces the water, okay? And then this group is located towards these polar heads of the phospholipid. It's here. So this hydroxy group is here, okay? And next portion is hydrophobic sterol ring, which doesn't like water. It's the true essence of cholesterol. And it is oriented parallel to phospholipid hydrocarbon tails. So it's actually sticking towards the center of the membrane. Now, why the cholesterol is important? It strengthens your membrane. What does it do? It actually is lodged between those kinks that you find inside the phospholipids. It prevents the phospholipid movement, the dance that they do all the time, and straightens the membrane. So it makes membrane much stronger. The next group I want to mention are glycolipids. Glycolipids are lipids that are attached to carbohydrates. So the lipid portion is inside the membrane. It does not like water. While carbohydrate chain will protrude out of the membrane. So these are glycolipids. Okay? So the glycolipids, again, lipids are inside the membrane, but carbohydrate is outside, and they're outside of the cell. And what are these? Is that their function is cell-to-cell interaction. They're also will tell you the structure of these glycolipids, and the carbohydrate chains will tell you on your red blood cells what blood type group are you. Okay? So they're involved in immune function and attachments of cell to cell. And they're also receptor for certain toxins. Toxins will use them, attach to them, and attack cells. So they are receptors for cholera toxin, of tetanus toxin, which we'll talk about later much more in detail. Let's talk about the second group of molecules that form membrane, and these are known as membrane proteins. They're very important. They provide function of the cell. So the first group of proteins are, look at this pink protein that you see here, big, and the blue one that you see, and this one that looks like a wind ribbon. These are transmembrane proteins. What's a characteristic for these? They span throughout the entire thickness of the membrane, from outside to inside, okay? So you see they span throughout the entire thickness of the membrane. And most of them contain several transmembrane regions known as alpha helices, which you're going to hear more later when we discuss some of the pathophysiology, specifically in Block 2. But you see that these transmembrane proteins span throughout the entire thickness of the membrane. They form, for example, ion channels. We're going to talk about in a second. Proteins also have their portions. They have a hydrophilic portion that likes water and it's oriented towards the outside environment. And they have hydrophobic portions that are more hate water, and they're in contact with these hydrophobic fatty acid tails of phospholipids. Another group of proteins that are there are something called the lipid anchored proteins. You see these purple blobs here on the image. These are lipid anchored protein, and yellow. Okay. So what is the characteristic of them is that they are actually attached to the lipids. They attach covalently to the lipid portion of the membrane, but they do not span throughout the entire thickness of the membrane. They are anchored in the leaflet of the membrane. So they're either anchored in outer or inner leaflet. Okay, they don't span throughout it. Now, both lipid anchor proteins and transmembrane proteins are known as integral proteins. You cannot remove them from the cell, so cell will not fall apart. They're very important, so they make cell wall. There's most important structures that maintain a cell wall integrity. And the next group of proteins is the peripheral membrane proteins. These are proteins that just peripherally touch to the membrane. Okay? So in this situation, the peripheral membrane proteins are inside the cell. Okay? So peripheral membrane proteins are inside the cell. What do? Look, they strengthen the membrane from inside. Okay? They're kind of scaffolding from inside that strengthens the membrane. Okay? So what do? They're located on cytoplasmic side of the membrane, and they attach to membrane lipids. But how do they attach to membrane lipids? They attach to lipid-anchored proteins, and lipid-anchored proteins are attached to the leaflet. Okay? So remember, they first attach to lipid-anchored proteins, and lipid-anchored proteins attach to the leaflet. So that is the characteristic of them. Good example is that the cytoskeletal proteins that form cytoskeleton. And in this situation, we're going to talk about that tomorrow. There is a protein known as spectrin that maintains the, for example, shape of your red blood cells. Red blood cells are biconcave, so their shape is due to the presence of spectrin inside it. The little protein that is spanning, attaching to the membrane, and holds these cells in a specific shape. So what's the function of the membrane proteins? There can be several functions. Number one, they can be cell adhesion molecules. Why? Because they can enable cell-to-cell contact. For example, blood cells can attach to the membrane proteins of endothelial cells that line your blood vessels. So they can get stuck on the wall of the blood vessel. They can be ion channels and transport protein, which means they can be channels for transport of ions. We're going to talk about in a few minutes. They can be ligand receptors, which means that they can attach to some signal from the outside, which will now induce the change in a cell, such as hormone coming from the side. They can be G proteins, which are inside, and you see here a G protein, and we're going to talk about that next week, which are secondary signaling molecules. So as the ligand attaches to the receptor will now stimulate the secondary signaling molecule that will send signals into the cells. So they can be that. And they, again, can be cytoskeletal proteins we mentioned that regulate the shape of the cell, and they also can, these cytoskeletal proteins can respond to signaling hormones. They can, cell can change its shape due to the stimulation from the outside. These proteins will change their organization. So let's look further into cell membrane structure and go back in it. So we know that cell membrane structure has two layers. It has bilayer arrangement, has two layers of phospholipids that has opposite orientation. There is a hydrophobic fatty acid tails that we see here. They're oriented towards the center of the membrane. So they face away from the polar environment outside. So what is the polar environment? What's the environment outside? It can be environment here in an inner leaflet. It can be a cytosol that has what? Cytoplasm has lots of water, so they're facing away from water. Or when you look with the outside environment, that can be interstitial space. It can be, for example, outside the cells, it can be blood, some cellular fluids, including lymph. So we see that these non-polar regions, these tails, are located between the leaflets. Hydrophilic portions of phospholipids are, you see these heads, they love water, so they are oriented towards the polar environment. So they will be facing the exterior and interior because that environment has a lot of water. Now, when we look at these leaflets, we'll have to understand that inner leaflets and outer leaflets have different composition. They have different phospholipids in them. So that's how you will recognize which leaflet. If you isolate the membrane in an experimental situation, you can actually identify which leaflet is what. Why? The outer leaflets will contain phosphatidylcholine and sphingomyelin. And they are found in the outer leaflet. While the inner leaflet will contain phosphatidylserine, phosphatidylethanolamine, and phosphatidylinositol. You remember what I mentioned, that they will not change their places. They will stay and remain in their own leaflet, except for one situation, is when cell undergoes apoptosis. So for all, I hope all of you remember apoptosis. If not, something I did a lot of research on, apoptosis is a cell suicide. Apoptosis situation when cell-headed pulls a gun and shoots its head, okay? Gets rid of and destroys itself because it might be infected by a virus, so it doesn't want to infect others. It might be abnormal, so it doesn't want to grow into the cancer, so cell will choose to kill itself. Apoptosis is the cell death that doesn't induce immune response. So if the cell dies, there is no immune response, there is no inflammation, nothing. Cell just dies. How does the cell signal local macrophages, other cells that eat the cells and foreign material, is they will change the structure of the leaflet. So what they're going to do is this cell will now pop this phosphatidylserine to the surface. Now the phosphatidylserine will go into the surface and pop out on the surface of the leaflet, which will now signal to other cells that cells have made a decision to die. Okay? And the cell will be destroyed. So another thing is we know that glycolipids are only found in the outer leaflet because they will kind of provide that surface on the cell. Think of it like hairs on the surface of the cell, glycolipids there. And then the peripheral membrane proteins are only found in the inner leaflet. We talked about this. Okay? So now, let's talk about a fluid mosaic model. What does that mean? That means that if you look under electron microscope, which is really cool, and you look at this live cell, not a fixed cell, which is not that easy, is you will see that the membrane is like a sea. It's constantly flowing. So the membrane is actually a sea, think of it, of the water. That surface of the water are the phospholipids. And inside you have those proteins bobbing in, okay? They're in there. These proteins that can be transmembrane or they can be actually peripheral proteins in it. And why is this? Simply because lipids can diffuse laterally. They can move laterally within the plane of the membrane. So what does that mean? These phospholipids can move laterally, but they cannot move between the leaflets. And that is important to see. So when you look at it, it looks like a mosaic, where you have the phospholipids, and then you have inside these proteins and other things that are floating in it. One structure I want to mention is lipid rafts. These are the more dense areas of that floating membrane. Those are the areas that have a lot of cholesterol. And what does the cholesterol do? Strengthens the membrane. So these areas of the membrane look like little rafts. They're much stronger, much more dense than the rest of the membrane. So the phospholipids within the rafts are extended. They're tightly packed, and there is a lot of cholesterol in them. What's a good example of the lipid raft are caveoli. Remember we mentioned those dimples that you see on the surface? They're actually a lipid raft. And what happens is that they are involved, as you remember, they're flask-like invaginations that contain a protein caveolin. And they're involved in the process of endocytosis and signal transduction that we mentioned. Let's talk about the membrane. One of the most important things that membrane does is not only to protect the cell, but it regulates the movement of ions and other things across itself. It actually regulates the movement from outside into the cells and inside out of the cell. So there are two types of transport that we're going to mention. Now let's go back to basic chemistry. What's a diffusion? Diffusion is movement of the ions across the membrane from the area of high concentration to the area of low concentration. So where you have more ions, they will move to the area across the membrane there is less ion. That is diffusion. It will follow a concentration gradient, the difference between concentration on two ends of the membrane. So the passive transport uses diffusion. What does that mean? It means that that's a random movement where actually you have more ions outside the membrane, this situation, a cellular membrane, less inside, and this concentration gradient will push these ions through the membrane inside the cell. This is known as diffusion. So this is the movement that is driven by concentration gradient, by the difference between concentration higher to the lower. It can occur spontaneously just across the membrane, or diffusion, it can have its own ushers. What does that mean? Is that ions will follow its concentration gradient, but they will come to the membrane. They'll be attached to the transport protein that will push them, carry them across the membrane inside, following their concentration gradient. So the movement, passive transport, is driven by kinetic energy. What's an active transport? Cell does that too. That's much more expensive. That's the one that cells has to put work in. Is this? It's the movement against concentration gradient. When a cell wants to move something from inside, for example, there is low concentration, to the outside, there is high concentration. So these ions want to flow from high concentration to low concentration, do they? But the cell wants to do opposite. She wants to push more from low concentration ions to high concentration against the concentration gradient. That uses energy. Cell needs to burn ATP to do that. Why? Because it needs to have a pump that will push that ion against concentration gradient outside. But this is known as active transport. The cell membrane is actively transporting components. Let's talk about diffusion. We mentioned diffusion is the spontaneous movement of the ions from high concentration to low concentration. And diffusion across the membrane can occur in two ways: through a simple diffusion or facilitated diffusion. So what's the simple diffusion? Simple diffusion means that the ions will follow their concentration gradient, but they were just simply going to go filter through the membrane and go into the cell. Just go through the membrane, okay? So that is a simple diffusion. So it occurs through the lipid bilayer, specifically if the compound is lipid soluble, can dissolve in lipids. Or it can occur through channels. If the cell has a channel, a little hole in it, that is specific to a certain ion, this ion will go from area of high concentration to area of low concentration across that channel. This is known as the simple diffusion. Now, of course, the movement during simple diffusion is affected by amount of substance. How much? What's that difference? You know, how big is the difference in concentration? They will be also affected by kinetic motion. How fast does it move? And the number and size of membrane openings. How many openings do you have? Facilitated diffusion, on the other hand, is doing this. It transports usually molecules that are too big to go through channels. And they cannot dissolve through membranes. So what does it do? There is a concentration gradient. There is more of this stuff outside than inside. But what's going to happen? There's going to be an usher. There's going to be a transport protein that will take this molecule, it's too big, and take it across the membrane and let it go inside the cell. So this is known as facilitated diffusion. There is somebody facilitating that diffusion, helping that diffusion up. This process doesn't require ATP. Why? Because there is energy. The ions want to move, for example, the compounds want to move from inside to outside. They really want to move. There is a concentration difference, but there is an usher that helps them do that. Or, you know, they will help them transport it. So let's talk further about the diffusion. First one is a simple diffusion. So simple diffusion you see here. Molecules will just cross the membrane. How they can do that? they have to be lipid soluble. They have to be dissolvable in what? In fat, in lipids, okay? Because then this molecule can just dissolve through the membrane and go into the cell. So what is transported through simple diffusion? Very important thing that keeps you alive every day is oxygen. Gases easily dissolve, and because they're nonpolar, and they can be easily transported across the membrane. So the rate of diffusion is really high. Oxygen, nitrogen, carbon dioxide are moved rapidly across the membrane. Next is channel-mediated diffusion. So if the molecule is not soluble in lipids, it cannot really dissolve in lipids, such, for example, as water. Water and oil don't mix. Water and fat don't mix. So how will you transport water across the membrane? Through a specific channel. And once there is a channel, the water will go easier through the protein, through this transmembrane protein channel, into the cell. So pores are composed of integral cell membrane proteins and are permanently open. However, these pores are not stupid. They will not be bouncers in some kind of, nightclub that they're letting everybody in, like underage, whatever. So what do? Is the pores are very selective. So pores will say, okay, I'm going to let this in, but I'm not going to let something else in. Why? Because they ensured, for example, they just look for polar molecules. That's why you have specific channels. They're specific for specific molecule that they will transport. Now, one example are good old aquaporins. Actually, these are water channels. These are channels in the surface of the cells that will transport aqua. They will transport water. Okay? Exclusive water channels. This is a very narrow pore that permits very rapid movement of water. But these channels are too narrow. They're really narrow for ions. So sodium wants to squeeze in. Sometimes they will. But the bigger ions can't really squeeze in through the channel. It's really tiny. Okay? So that is the characteristic of these aquapores. Now, what's a characteristic also for them is that number of aquaporins on the surface of the cell can change depending on hormones. Hormones can tell the cell, I want you to be more leaky for water, or I want you to be less leaky for water, so you're going to have more aquaporins or less aquaporins. One of the hormones that does that is known as antidiuretic hormone, and we're going to talk about that later in block 2. So now let's talk about some cool channels. Let's talk about selectively permeable channels that just selectively allow passage of specific ions into the cell. So first one is a potassium channel. Look at it. This is really cool. It actually allows the passage. This is a potassium channel. It allows passage of potassium 1,000 times more than it allows the passage of sodium in it. It's very selective for potassium. So how does it work? It has tetrameric structure, which means 4 large protein subunits. You see them here. These one in the center, in this situation, the channel is closed. These large protein subunits are kind of closing the channel. Okay? Now what happens? They will also have pore loops that form something called a selectivity filter. They will test what's going into the channel and check whether channel will open or not. They are the bouncers. Okay? So these are the selectivity pore filters. These are known as pore loops. You see them here on the side. And they're lined up with another molecule known as carbonyl oxygen. So how does this work? Here I am, a potassium, all attached to water, okay, because I'm in a water environment, and I want to go into the cell. What do? As a potassium, hydrated potassium will enter this selectivity filter between the pores. Now, the potassium and water will go into this selectivity filter in the pores, and now what's going to happen is that the water will be removed from potassium by the action of carbonyl oxygen. And what's left is pure potassium. Now this reaction will now cause conformational change of the channel, and these two ends will move laterally and will allow potassium to go in. Okay? So that is the selectivity filter that it is. Now, sodium ions are actually too small to pass through this channel because they will not even attach to the selectivity filter and they will not open the channel. So channel only opens for potassium. Now let's talk about sodium channels. Sodium channels are very small openings because sodium is very small. And these very small openings are lined up by very negatively charged amino acids. So these strongly negatively charged will attract sodium attached to water into the channel. As the sodium attached to water goes into the channel, the water will be removed out of the sodium, and sodium will now follow its concentration gradient and will go into the cell. Now, what is a characteristic of these channels is that they have little flaps. They have little doors, okay? So they can be open or they can be closed, okay? So these are known as voltage-gated channels. What does that mean? If the voltage of the membrane is high enough, if it's more positive, it will open a channel. When it opens the channel, sodium will go into the cell because it's going to follow its concentration gradient. So these are regulated by the membrane potential. So these sodium channels are inhibited by tetrodotoxin. Okay? So the sodium will not be carried into the cell. Sodium will not now activate the cell, cause action potential, and contraction of the muscles is going to cause paralysis. So these are voltage gated. That means they have little gates that open depending on the voltage of the membrane. So let's look at the gating of the protein channels. How does that work? So protein channels are distinguished by two important characteristics. Protein channels are selective. We talked about it. They will not let Dr. D into a cool club, okay? Because they're selective. They're going to say you have a geeky, for example, tie, okay? So they're very selective, okay? So they select what they're going to let go through it. And they can be opened and closed by gates. So there are gates on it that can open and close, allowing the passage of ions. So what regulates the gates? Electrical signals. If the membrane potential, for example, is high enough, more positive, this will result swing opening of your sodium channel gates, and a sodium will go into the cell. Okay? Or they can be chemically or ligand gated, which means there is some molecule, some little signal that's going outside the cells, can attach next to the gate and open a gate, allowing the molecule to go through. So these are chemical or ligand gated channels. So you have two types of channel. You have electrical and you have chemical. Let's talk about facilitated diffusion. So what is the facilitated diffusion? Remember, the molecules are following their concentration gradient. They're going from high to low concentration, but they have ushers. Okay? Something is happening, but they're too big to cross the membrane. So this is the facilitated diffusion. So substances will diffuse through the membrane using specific carrier protein. And this protein will facilitate the transport of these molecules across the membrane. How will you recognize which which transport is facilitated or which transport is just pure diffusion? Okay? And this is what they're going to ask you on your board. I know you're going to remember it for the boards, but you're going to see this. They will give you this curve, and they will tell you which of these two, just an example, which of these two channels is facilitated diffusion. Okay? It is the red line. It's the red channel. Why is this, guys? Think of this. You have concentration gradient. There is no facilitation. What's going to happen? Ions will just flow and flow and flow until they equalize the concentration. And you see here, ions are flowing and flowing and flowing. Higher concentration outside, more ions flow in. However, if you have facilitated diffusion, that doesn't matter. What does that mean? Is you increase the concentration of ion outside. You put 10 grams of sodium outside. Just an example, it's not sodium, but something else. Sodium doesn't use the transport. But what it is you put a lot of, there is high concentration gradient. But diffusion will occur and then it will reach maximum velocity. And it's not going to go further. Why? Because all those ushers are busy. So you can add as much as you want outside people to get into the club, but ushers are busy. Okay? So all the ushers are busy. They're doing this. So that's where the facilitated diffusion will flatten out. The concentration, transport, velocity of transport flatten out. Now we know how does this facilitated diffusion works. The molecule needs to be transported, will enter the transport protein in the membrane, and will bind to its receptor. Will bind into receptor. Now, binding of the molecule to receptor will change conformation of that channel, and this channel will now open and release that ion into the cell. But it actually is not using any energy. What's an active transport? Now, this one is expensive, guys. The active transport is working against the concentration gradient, and you do it all the time. Right now, your cells are doing it. So what does that mean? Is that it's a movement of ions against their concentration. So they go against the gradient, concentration gradient inside the cell. So they move from lower concentration to high concentration. They work against the gradient. So there is two types of active transport. There's a primary active transport that actually uses the energy from the breakdown of ATP. What does that mean? It burns your money. It burns your cash in a cell in order to move stuff out. But the second transport is kind of cool. What does it do? It actually hitches a ride. What does that mean? Is that one molecule will move into the cell following concentration gradient, but the other one will use that energy and will hitch a ride and will pull back against concentration gradient. So one is going in, another one is using that energy of the transporter to be pushed out against the concentration gradient. So this is known as secondary active transport. It means that uses somebody else's energy of movement. But in both situations, they do have to have proteins that enable the transport. This is the most important pump in your body. You know, this is the pump. Every morning you wake up, you should say, "Thank you, sodium, potassium pump, I'm still alive." Okay? That is true. It's the pump that constantly makes your cells survive. It's one of the most important pumps in our body, and what does it do? It actually does this. Look, it's a secondary active transport. Okay? It moves out 3 sodiums for exchange for 2 potassium. Okay? But both sodiums and potassiums are moved against their own concentration gradient. So they move against where they should be moving. So what does that tell you? What does this pump needs to use to move them? ATP. So these pumps are constantly burning your precious fuel. Okay? These are the pumps that are constantly working against concentration gradient, moving 3 sodiums out in exchange for 2 potassiums. 3 positive out in exchange for 2 positives in. I'll tell you why that is important. Remember, 3 out positives, 2 in positives. So what does that leave us with? 1 less positive inside. Does it? 3 out, 2 in. So what does that tell you that what's going to happen inside the cells? Inside the cell is become negative because we have extra sodium pumped out, extra positive. That makes cells negative. So how do they do? 2 potassium ions bind to the outside of the carrier protein. 2 sodium ions bind to the inside of the carrier protein. Now ATP is used, and ATP will be broken down into ADP, that phosphate will be used as energy. And this sodium, the protein transporter will change its conformation. It's almost going to flip. And when it does that, 3 sodiums go out and 2 potassiums go in. Why is this pump important? It actually uses 60 to 70% of energy of your brain just to maintain these pumps. So because they're constantly maintaining that negativity inside the cell. Interestingly, this pump can work in reverse, but I'm not going to bug you with this because now we're going more into some things that you're not going to see in your patients. It will never work in reverse in normal situations except in serious pathological situations. Very important, again, is that they will transport this. So what's the role of this pump? Controls the cell volume. What does that mean? What are we pumping outside? 3 sodiums for exchange of 2 potassiums in. What follows sodium? What really loves positive is water. So water will follow that sodium, and the cells will be prevented. This water will get out through the aquaporin channels out. This will prevent cells swelling of the cells. So if this membrane stops, this transporter stops, cells swell, explode, break in pieces. Okay? Also, it's an electrogenic function we already mentioned. 3 sodiums out for 2 potassium. What remains in the cell? negative charge, so they maintain a negative potential inside the cell. Let's talk about hitching a ride. So this is the secondary active transport or co-transport, where you have two molecules. One is following its concentration gradient, other one is going against its concentration gradient, but is hitching a ride with the first one, okay? We mentioned this. So this is, for example, is the sodium glucose co-transporter, or sodium amino acid co-transporter. You're going to hear about this from Dr. D way later, in very important in GI Phys. But this transporter, what does it do? Look at this. Is you have a transporter, sodium is following its concentration gradient. It's going into the cell from high concentration to low concentration. And it attaches through a transporter from the outside. Glucose, however, is going against this concentration gradient, okay? There is more glucose inside the cells than it is outside, okay? So the glucose is going against its concentration gradient. So they both bind to transporter to the outside. Sodium will move following its concentration gradient and will change the conformation of the protein. And at the same time, glucose will use that energy to be pumped against this concentration gradient. Does it make sense? Sodium follows concentration gradient. Glucose does not, but it hitches the ride together with sodium to get into the cell. That is a very important mechanism for absorption of glucose in your body in your intestines, okay? So that is very important. What do you have? Sodium follows concentration gradient, binds to the transporter. Glucose also binds to transporter. Sodium enters into the cell following concentration gradient, and glucose hitches a ride with it, okay? And goes into the cell too. So this is known as secondary active transport. We mentioned it, where one molecule is going against concentration gradient, following the molecule that follows concentration gradient. Counter transport. You know, if you watch the movie Hangover, I call this a classic switcheroo. And if you remember Mr. Choi, who is a proud graduate of University of North Carolina, the actor. But what it is actually two molecules going in opposite direction. One is going following its concentration gradient, the other one is going against its concentration gradient. So this example is sodium calcium and sodium hydrogen counter transport, move in two different opposite directions. So we see here, sodium will attach to the outside of the transporter, and calcium will attach to the inside. Calcium is going against this concentration gradient, while sodium is following its concentration gradient into the cell. So what's going to happen is as sodium binds outside and calcium binds inside, the protein will change its conformation using the energy of sodium going into the cell. Because sodium is the one that's driving this game. Sodium is following its concentration gradient. And as it does this change in conformation and this use of this energy will pop calcium out of the cell. So one is going in, another one is going out. So this is also a very, very important mechanism. We're going to talk about it later in Phys. So a good example, again, is sodium, hydrogen, calcium countertransport. Okay, guys? That's pretty much it. So just few things to tell you about. I know it's your first week, and you're getting used to the way of learning material. I will tell you how I operate. Is please understand that you're responsible for material on the slides. You don't really need to read the book, because my slides follow the book. However, if you don't understand something and you don't want to bug poor Dr. D about it, and I'm joking, no worries, bug me. My question is whether I answer or not. Just joking. That's my humor. Don't worry about it. But what it is that book can help you clarify certain concepts. However, what are you responsible for your exam and knowing this? Trust me, guys, we're going to talk about this probably 10 times before you go out of next 2 years, and you're going to hate it. But right now, what I want to do is I want to kind of give you an overview and clinical association. As you know, this lecture has not much of the clinical correlation, so I might ask you here basic stuff about transporters. However, wherever there is a clinical correlation, focus on it. Because you're in med school. You know, I'm not here to ask you how much ATP is spent doing this. I don't want to. The other thing is I sat in your benches. I'm an MD PhD. I went through med school. I know what really you need for medical school. So what I want you to use the knowledge from my lecture in a clinical case scenario. And it will involve the disease that I have given you. Okay? It does not, I'm not going to test you on diseases you haven't had yet. That's not fair. Okay? And you haven't had yet pathology, all these things that come up later. So please be aware. So most important, just go through my slides, look at the clinical correlation, be comfortable with them. I have a policy that just before the exam, what I normally do is I will give you some questions to work on. And I don't want to give it to you right now because you're going to freak out. Okay? But I'm going to give you some questions, and this is Exam Master program that Dr. Kuo also uses, which is really cool. You all have access to it. So it's kind of, you can self-test yourself, okay? Just before the exam. So I'm going to provide this for all of you guys. The thing with this is it's not graded. Do it, don't do it. It's up to you. And the questions have not been written by Dr. D. So I stand behind. If there is some question that sounds weird, don't chase me, okay? But it's really good. It's actually thousands and thousands of questions that are board related or at least related to material we teach. And that's what I'm going to provide for you a week before the exam. I don't want to give it to you right now. So that will kind of give you a chance to kind of go and test yourself. Some of the questions will be, boom, boom, what's this, what's that? You'll be very happy. And if you're comfortable with that you'll be fine with my stuff, okay? Don't freak out. Another thing is, I don't know if anybody told you, quizzes are great things. As much as you're afraid of quizzes and maybe it's a new concept for you, it's a great thing for you to see where you're at, okay? So please understand that quizzes are a portion of your grade. Don't get straight A. You should improve, but you shouldn't go and jump out of this building. It's not going to help you. We're really low. But what it is the idea of quizzes, and we build this with attention. But the thing is, you know, quizzes are a great opportunity for you guys to kind of gauge your knowledge, makes sense, and you see where you're doing well or not, okay? So to move on. Now, if you're on your 5th quiz failing, then we're in trouble. Houston, we have a problem. But if you're on the first one not doing exactly how you want, you know, please understand you can go to your advisor, you can sit down with your colleagues, kind of figure out what's missing. You don't have all the same experience, you don't all have the same education, background, that's fine. That's absolutely okay. You know, my background was in, I was a geek group, and my major was physics and mathematics. And I hate mathematics, just to tell you. That helped me to understand how much I hate mathematics. So that is the idea. So please be aware of this. That helps you kind of get into, and do this mock exam. I think it's an awesome idea. Thank you very much, guys. See you.